This is the quick presentation of our paper, FrustumFormer, Adaptive Instance-Aware Resampling from Multiview 3D Detection. In this paper, we focus on the task of multiview 3D object detection. Recent approaches mainly focus on the design of view transformation, answering the question of how to transform view feature. However, choosing what to transform is also important, but has rarely been discussed before. The pixels of a moving car are more informative than the pixels of the sky. To fully utilize the information contained in images, the view transformation should be able to adapt to different image regions according to their contents. We propose a novel framework named FrustumFormer, which adopts two types of queries to transform the BEV feature. Instance queries are sparse and irregular, focusing more on instance regions, while scene queries are dense and regular, learning global context information. Comprehensive experiments on the NU scenes dataset demonstrate the effectiveness of FrustumFormer, and we achieve a new state-of-the-art performance on the benchmark. Hi, my name is Yuqi Wang, a PhD student from the Institute of Automation, Chinese Academy of Sciences. This is the presentation of our paper, FrustumFormer, Adaptive Instance-Aware Resampling from Multiview 3D Detection. Camera-based 3D object detection has earned a wide audience, due to the low cost for deployment and advantages for long-range detection. Recently, multiview 3D object detection in bird's-eye view has made fast progress. Due to the unified representation in 3D space, multiview features and temporal information can be fused conveniently, which leads to significant performance improvement over monocular methods. In this paper, we focus on the task of multiview 3D object detection. Multiview 3D object detection aims to predict the 3D bounding boxes and categories of the objects with multiview images as input. Transforming perspective view features into the bird's eye view is the key to the success of modern BEV 3D detectors. So how to transform view feature? Current methods can be divided into two schemes, 2D lift 3D and 3D query 2D. The transformation of features from 2D perspective space to 3D space is essential to multiview 3D object detection. Recent approaches mainly focus on the design of view transformation, either pixel-wisely lifting perspective view features into 3D space with estimated depth or grid-wisely constructing BEV features via 3D projection, treating all pixels or grids equally. However, choosing what to transform is also important, but has rarely been discussed before. The pixels of a moving car are more informative than the pixels of the sky. To fully utilize the information contained in images, the view transformation should be able to adapt to different image regions according to their contents. We propose a novel framework named FrustumFormer, which pays more attention to the features in instance regions via adaptive instance-aware resampling. As shown in the figure, FrustumFormer is composed of four components: an image backbone, a Frustum encoder, a Frustum fusion module, and a detection head. Our core design lies in the Frustum encoder and Frustum fusion, which exploits the geometric constraints behind perspective view and bird's eye view by instance Frustum. Instead of treating all regions equally during the feature view transformation, our Frustum encoder adaptively transforms the image features according to the view content. We adopt two types of queries to transform the BEV feature. Instance queries are sparse and irregular, focusing more on instance regions, while scene queries are dense and regular, learning global context information. The learning process of the scene query is similar to BEV-former. However, the instance queries are learned inside instance regions, and the learned instance feature is further combined with the scene feature to form the final instance-aware BEV features. Next, we will introduce more details about our method. As shown in the figure, instance queries are in yellow color, generated from irregular instance Frustum, while scene queries are in blue color, generated from regular BEV grids. The selection of instance queries is made via adaptive instance-aware resampling, which consists of instance Frustum query generation and Frustum occupancy mask prediction. In instance Frustum query generation, we take advantage of object detection on the image plane and leverage its instance Frustum on the BEV plane to select the instance Frustum queries. Although the instance Frustum provides potential locations for objects, its corresponding area on the BEV plane is often large due to depth uncertainty. To reduce the localization uncertainty, we propose to predict an occupancy mask for all Frustums. The occupancy mask can get supervision from the projection of 3D bounding boxes on the BEV plane. We define instance Frustum cross-attention to compute instance features between instance queries and image features, and temporal Frustum cross-attention for temporal fusion. We adopt a sequential RNN way to fuse the history BEV features. Comprehensive experiments on the NU scenes dataset demonstrate the effectiveness of FrustumFormer, and we achieve a new state-of-the-art performance on NU scenes test val set without extra LiDAR supervision. In the ablation study, we first ablate the components in FrustumFormer. Utilizing adaptive instance-aware resampling, IF plus OM, and temporal frustum fusion, FF, can significantly enhance performance. The next experiment proves the effectiveness of instance-aware sampling. Compared with B and C, we found that instance-aware sampling is more effective since simply increasing the sampling points for all regions has no gain. We also ablate the hyperparameters used in occupancy mask learning and temporal frustum fusion. It indicates that longer temporal fusion will improve detection performance. With adaptive instance-aware resampling, our method shows recall improvement under low visibility. We found that the recall for categories of bicycle, trailer, bus, and construction vehicle improved a lot under the low visibility. Since nearly 29% of objects belong to the visibility of 0 to 40%, such improvement is crucial for a better 3D object detector. We provide some visualizations for the case of recall improvement. The red circle indicates the region where air helps to discover objects that were previously missed by enhancing the learning of instance features. As shown in the figure, we illustrate the instance-aware sampling points of our method on both image view and bird's eye view. The sampling points are highly related to the instance regions. Our method can also be intuitively explained through the heat maps of BEV features. The BEV features learned by our frustum encoder is instance-aware and has strong relations to the real positions. We compare the BEV feature between the baseline and the baseline with adaptive instance-aware resampling. Here we visualize the corresponding ground truth boxes on the right side. When utilizing air, more instance regions would be discovered, corresponding to the recall improvement, and the features are more instance discriminative in the dense areas, as shown in the yellow box areas. Thanks for your listening. We provide the paper link and code link below.